Hello teacher, I'm Phước from Group 10. Today we will talk about chapter 12, Threat Control. There are 12 sessions in this chapter. I will talk about session 1 to 4. Harmful and Totally will present the rest. Let's come to the introduction. In this chapter, we will dive deeper into threat control, exploring threat attribute and situation primitive. We will also discuss how threats can maintain private data within the same process and examine the interaction between process-based system call and threats. Let's talk about threat limits. The threat limit can be queried using syscall. The syscall function can be used to query threat-related system limits, which are crucial for application portability across different operating systems. Threat limit and name argument to syscall symbol like threat statement and threat mark. Uh, statement is can minimum number of bytes that can be used for a threat stack and argument of that is threat statement threat mark maximum number of threads that can be created in a process and argument of that is SC thread mark. I have these two argument in my demo code. Let me show you. Here I have a virtual machine that run on Linux. I have write down the code already. Uh, we have two key variables that is mark thread and stop size. Um, and the two argument SC thread mark and SC thread stop min. I have show you the variable mark thread. This variable holds the maximum number of threads that the system allow and stop size. This variable holds the minimum stop size that it threaded. I will run the code. Here's the result. It says that max number of threads is -1. It means that um, the system uh, maximum number of threads depend on factors such as system resource, like memory, CPU, and operating system configuration. Many modern operating systems do not have a fixed limits on the number of threads, but will adjust based on the system capability. And the minimum stack size per thread is 16,384 bytes. It is 16 kilobytes. And this is the smallest amount of memory that the system require for each thread to operate. Back to the presentation. We have thread limits and name argument to syscall. We have limit on some operation. The tool has shown you thread key map is 1024 and thread stack min That answer I have told you that is 16 kilobyte. Uh, the result from that demo so that you can create an indefined number of threads depending on your system resource, and each thread will need at least 16 kilobyte stack mean memory to operate, but you can increase the stack size if need for more complex stack. Here, the stack mark is no limits. Knowing the value is important because each operating system has different limits and applications should be written to respect the limits to ensure portability and stability across different platforms. Next, we talk about thread attribute. POSIX thread attribute allow customization of thread behavior. Attribute include data state, word size, stack arrest, and stack size. Functions that is pthread RTCR, init, initialize attribute, and pthread RTCR destroy attribute. I have write a code here that have the RTTRT that is key variable and pthread relay. Uh, pthread RTTRT 6 is a thread attribute object that how customizable attribute like stock size, data state, I have told you, and create it. This function is used to create a thread using the initial line attribute, and I will run the code. It's called running, and this is the result. We have thread 1, 2, 3 evening, and then finishing that is initialize and then destroy. In pthread RTTRT initialize thread attribute with default value, which can be modified to customize thread behavior, uh, and then destroy using pthread RTTR destroy uh, to free up the resource allocated for the thread attribute when they are no longer needed, helping to prevent memory leak. Next is thread attribute data state. Control whether a thread resource are released immediately upon termination. There are two states. First is joinable. Thread wait for another thread to join before resources are released, and the task thread automatically release result after termination. Stack management. Stack size specifies the memory size allocated for stress stack. Stack address allows setting a specific memory location for the stack. Correct stack. Word size provide additional protection memory to prevent stack overflow. Synchronization attribute mutex attribute protect share attribute determine if a mutex can be shared between processes. Robust attribute ensure mutex recovery if the owner thread terminate while holding the mutex function. We have to that it be thread, mutex RTTR and INIT and be thread, mutex RTTR destroy. Here's the demo course. Um, we have pthread mutex t mutex. This is a mutex offset due to protect shared data from concurrent access by multiple threads, and then share with data. Um, share with data. Um, um, I will run the course. It says that final value for saved data is 200,000. Mm, uh, a multi-tech is a synchronization mechanism that ensure only one thread can access a critical section of code at one time. When a thread locks the mutex, uh, the thread mutex lock other thread attempting to lock it are forced to wait until the mutex is unlocked, and then unlocked. In a multi-thread environment, shared data can be corrupt if accessed simultaneously by multiple threads. The mutex protects shared data by allowing only one thread to access it at any given time, preventing write conditions. Next, we will talk about reader writer lock attribute. This attribute used to manage concurrent access where multiple readers can access simultaneously, but writer needs exclusive access. Reader writer lock attribute can be customized similarly to mutex function. Epthread reader writer lock ITTR INIT and pthread reader writer lock ITTR destroy. Like also I have write down code already, and we have um, pthread reader writer lock reader writer lock, and then this is with the writer lock offset that manage access to share resource for with the writer, um, and then unlock it. um, the writer lock. This function acquire the lock for writing, ensuring that only one writer can modify the share resource while no reader are active, and Let's run the code. Here we can see we have reader and writer with the code only so finish if only the read or the reader and writer is finished they reading and writing here writing and then finish writing and finish mm, reading and then finish reading. We will move to the last one, condition variable and barrier attribute. Condition variable facilitate waiting and signaling between threads. Process share attribute can be used for inter-process condition variable barrier used to synchronize a group of threads at a specific point. Custom attribute to control process sharing. I have a demo of condition barrier here. Mm, we have key variable pthread conditional check con. Check is the condition variable that thread wait on until a specific condition is met. As pthread barrier T barrier check is the barrier that force thread to wait until all other threads reach the barrier before proceeding, and pthread mutex the mutex Sig mutex is used to protect the safe variable ready and to ensure that only one thread modifies it at a time. And the ready this safe variable indicates when threads are allowed to proceed after receiving a signal from the condition variable. Because the error ensures that all threads in a group reach a certain point in the code before any of them proceed further. SIG is useful for synchronizing multiple threads, and the condition variable allows the rest to wait for specific event to occur. When the condition is met, one or more threads can be signaled to proceed. Let's try running because here the thread 1 is waiting 1, 2, 3 is waiting as bearer, and 2 the our thread has passed the barrier. The signal or thread to proceed uh, it allow thread to come in, and then thread doing it network uh, was seeking after condition variable and then of this um, error are useful for ensuring synchronization between threads, while condition variable allow for more complex coordinate, such as waiting for specific condition to be met before thread can continue the execution. That is the end of my presentation. Thanks for listening.
My section today covered thread synchronizations, attributes, and thread safe programming concepts. We will particularly focus on reader graded lock, conditional variable, barriers, and reentrancy. These synchronization mechanisms can crucial for controlling how threads interact with shared resources. These synchronization mechanisms can crucial for controlling how threads interact with shared resources. So let's dive into the first concept about the reader and writer locks. The reader and writer lock are designed to efficiently manage access to shared resources in situations where read operations are more frequent than write. So this type of lock allows multiple threads to read the resource simultaneously but restrict write access to only one thread at the same time. This improves performance for the read-heavy workloads. And the functions for reader and writer lock are the initialize the reader and writer lock attribute using the pthread rw lock ATCR init and the destroy for clean up the attribute after use. And both of these functions return 0 on success and an error number if there is a failure. The only attribute supported by reader and writer locks is the process share attribute, and this attribute controls whether the lock is shared between threads within like a single process or even across the multiple process. The function to manage the process share attribute are the getShift for get the current value of the process share attribute and the setShift for set how threads share the lock across the processes. This is particularly useful in inter-process synchronizations where we want multiple processes to coordinate access to shared data. The supported values for this attribute are the pthread process shared for sharing across multiple processes and pthread process private for restricting use in a single process. Next, we will talk about condition variable. Condition variables are used to block a thread until a specific condition is met, coordinating the timing of the thread execution. Much like mutations and reader graded lock, conditional variable can customize using attribute. The functions for conditional variable attributes are like pthread condattr init for initialize the attribute and pthread condattr destroy for clean up the attribute. Conditional variable has two attributes defined by the single Unix specification. They are the process share attribute and the clock attribute. The process share attribute, similar to other synchronization primitives, while the clock attribute controls the timeout behavior during timed waits. The clock attribute specifies which clock to use for time waits. For example, we have the clock real-time used for system while lock, and the clock monotonic used a clock that isn't affected by the system time changes. And functions to manage the attribute, we have the pthread con attd get shape and set shape for managing the process share attribute. Also the pthread con attr get clock and set clock for managing the clock attribute. And a little note that the clock attribute is very important for application where timing is crucial. Now let's discuss the barrier. Barriers are synchronization points that thread must stop and wait until all threads has reached the same point. So barriers ensure that threads project together in phase. The process share attribute for barriers works similarly to the attribute we see in reader write lock and also the conditional variable. It has its own functions, include the pthread barrier attr init for initialize the barrier attribute and the pthread barrier attr destroy for clean up the attribute when we no longer need it. Also, we have the get and set process share attribute for barrier with get shape and set shape. The last sections I want to talk about today is about the reentrancy. The reentrancy is crucial in multi-threaded environments where multiple threads may call the same function at the same time. Like reentrancy is a property of a function that allows it to be called by multiple threads without causing any data corruption or inconsistent result. A reentrant function doesn't rely on shared static data, and it avoids issues that arise when multiple threads try to access to move or modify at the same time with the same data. The reentrant functions are a subset of thread-safe functions. So a thread-safe function is one that can be safely called by multiple threads at the same time, but not all thread-safe functions are reentrant. Some thread-safe functions rely on internal mechanisms like locks can block or slow down execution in a multi-threaded context. On the other hand, the reentrancy ensures that a function can be called concurrently and even from within signal handler without causing any unexpected behavior. However, not all the functions are guaranteed to be thread-safe, as shown in the stable functions like SNV or SDRTalk and local time are not guaranteed to be thread-safe. This is because these functions use static buffers that are shared across multiple threads, which can lead to unpredictable results if called concurrently. And to address these issues, the POSIX provide thread-safe versions of many of these functions, as seen here in the figure. These functions are marked with an R suffix like get, NV, R, and local time R. In these versions, the caller provides their own buffer, so each thread deals a separate space in memory, avoiding the interference from other threads. Another way to ensure thread shape is by using lock. For example, static I/O functions like fopen, fquiet, and fclose can use the flock file and ftry lock file function to lock the file object. Dealer lock prevent multiple threads by manipulating the same file at the same time, so it avoids the risk conditions. But sometimes there are the overhead of locking, and to reduce the performance overhead of locking, the POSIX provide the unlocked I/O functions like getChar unlocked and putChar unlocked. The other functions bypass internal locking mechanism. They must be used carefully, and we need to manually lock and unlock the file object when call this function to prevent unpredictable results due to the concurrent access. Now let's look at an example of a non-agent functions. Get_env is shown in this code. The get_env store is result in a static buffer. If two threads call this function at the same time, they will both use the same buffer, and potentially leading to inconsistent results or corruption. So to make GenTip reentry, we can modify it so that each thread provides its own buffer, as shown in this example of get_env. Or this version also uses a mutex to lock access to the shared environment list, ensuring that only one thread can modify at a time. And this makes the get_env both thread shape and reagent. However, just making a function thread shape doesn't mean it's reagent in all contexts. For instance, the signal handler can interrupt the flow of execution in a program. If a signal handler calls a function like get_env while it is being used, it could cause the deadlock if the function is holding a lock. So to avoid this, we use the recursive mantis, which allow the same thread to acquire the lock multiple times without blocking. And this will prevent the deadlock scenario when a function is interrupted by a signal handler. So this is the end of my part. Let's move to the next part with my teammate Nguyễn Thị Châu Thi.
Hello everyone, my name is Jyoti and today I will talk about thread-specific data. This is a critical concept in multi-thread programming, allow each thread to store and access its own data. By doing so, each thread can operate independently without being affected by data from other threads. In a multi-thread process, all threads share the same address space. While this is efficient for shared resources, it can sometimes lead to data conflict. And thread-specific data provide a solution by allowing threads to have their own private copies of data. A well-known example is Erno variable, which store error codes generated by system calls in a multi-thread environment. Each thread must have its own instance of error to avoid overriding error caused by other threads. And to manage the specific data, we primarily use the function. The first one is pthread_key create. It creates a key for associating data with each thread. The second one is pthread_set_specific. It assigns data to current thread using the create key. And the last one is pthread_get_specific. It retrieves thread specific data using the key. And in a multi-thread environment, if multiple threads attempt to create a key at the same time, errors can occur. So to prevent this, we use pthreads1, which ensure that key creation function are called only one, and no matter how many threads are running. The destructor function is assigned during the creation of the key using pthread key create. This function is automatically called when a thread terminates to a free resources associated with a thread-specific data. So this is an example of a destructor. This ensures that memory allocated for thread-specific data is properly free when the thread exists, it preventing memory leak. So now let's move to the demo where I will show how we use thread-specific data to build a thread-safe get environment function. Now let's run this code. You can see here, each thread brings out a message contain a thread ID and the path environment variable. This so that the threads are up and running and doing their job properly. So you can see both threads bring out the value of the path environment variable. This means that the get function has correctly performed its step of getting the value of the path variable from the environment for each thread. So in the part, we discusses the importance of thread-specific data in multi-thread programming, and we saw how to create and set and retrieve thread-specific data, and we demonstrate its use through a thread-safe version of the getEnvironment function. By using this technique, we ensure that each thread can maintain its out So in this part, we discusses the importance of thread-specific data in multi-thread programming, and we show how to create, set, and retrieve thread-specific data. And now we demonstrate its use through a thread-safe version of getEnvironment function. By using the technique, we ensure that threads can maintain its out private state, avoiding conflict in shared resources. And let's move to the next one. I will present an important topic in multi-thread programming, cancel option. We will explore how these options work and how they affect the behavior of threads. First, the cancel option defines how a thread can be canceled using the pthread cancel function. There are two main attributes we need to focus on is cancel state and cancel time. Cancel state, about cancel state, this attribute either allows or prevents a thread from being canceled, and cancel time, this attribute defines when the threads will actually be canceled. About the cancel state can be either a pthread cancel enable or a pthread cancel disable. In the default state, pthread cancel enable, the thread can be canceled. When switched to pthread cancel disable, the cancellation request will not be executed immediately, but it will wait until the state is enabled again. So we can train the cancel state using a pthread set cancel state function. About cancellation points, a thread check for a cancellation request at a specific cancellation point. Certain functions such as pthread join and read are defined as a cancellation point. If a thread does not call any cancellation point function for an extended period, we can use a pthread test cancel to check our pending cancellation request. So now I will show a simple demo code so we can know how the cancel option work. And now I will show a simple demo code to know how the cancel option work. The code create a new thread that bring information in loop and can be cancel when we call pthread cancel. So pthread set cancel state here is allow the thread to be canceled. Pthread test cancel is the cancellation point where the thread check for cancellation requests and prepare to terminate if any. And now we will run this code. This first line is bring thread started. So after calling a pthread create, a new thread is created and bring this line. That means the thread has started executing. Thread is running. The thread is continuous run and bring this line every second. It's an infinite loop and with a cancellation point added via pthread test cancel function. So this allows the thread to check for the cancellation request. Sending cancel request. So after main have run for 3 seconds, it's called pthread cancel to send a cancel a request to the running thread. This request calls the thread to check the cancellation point from pthread test cancel and prepare to terminate and thread cancel. After cancellation request is sent and a thread successfully check for the cancellation point, the thread is canceled by a pthread join and wait for the thread to terminate, then print this line. It means that the threads were successfully terminated. And next, we will explore how a fork function operates in a multi-thread environment and how we can effectively manage the state of multi-thread after a fork using pthread fork. So when a multi-process call fork, only the thread that involve fork is duplicated in a child process. All the threads are not copied. This creates a challenge while the child process inherits state of multi from parent. It doesn't know which lock are held by parent. So this making it impossible to unlock them correctly. So we have a solution to address the issue that arise with multi state during a fork. We can use the pthread fork function. This function allows us to set up 3 types of handler. The first one is the prepare handler. It's lock all the necessary multi before the fork occurs. And the parent handler is lock those multi in the parent process after a fork had happened. And the child handler unlocks the multi in the child process after the fork. So now let's look at an example. Here is a sample code. We will know how to use the pthread fork. So now let's look for a sample code. We use the pthread fork In this code, we verify to bootc log1 and log2. This prepare handler log this. So now let's look a simple code that we use a pred fork. In this code, we define two bootc log1 and log2. The prepare So now let's look at simple code that we use pred fork. In this code, we define two bootc log1 and log2, the prepare handler. That log this bootc while the parent and a child handler unlock them currently. So we run this code. You can see here, the parent is about to fork. This message means that the parent process is prepared to fork and preparing to lock. The parent process called the repair function. So here's this one. So prepare to lock. The parent process called a repair function, which log to bootc log1 and log2. This ensures that while the parent process is doing some work on the shared resources, no child process can join and cause data conflict. Parent unlocking. So once the parent process have finished doing the necessary work with bootc, it unlocks them. So this allows all the processes, including the child process, them can access to the bootc is necessary and ensure that the shared resources can be used safely. While parent have returned from fork, this line means that the parent process have returned from the fork command. This means that the parent process has successfully copied its state and now continue to operate in both parent and a child processing. Child unlocking. After child process is created, it unlocks the bootc inherited from the parent process. Without the pthread fork function, the child process would not know the status of the bootc in a parent process, and it could cause the deadlock if both processes try to lock in bootc. So about child has returned from fork. This line means that the child process has conflict a return from the fork command. It means that the child process is now independent and ready to perform its own task. So next, we will discuss the pthread and pwrite function, which are essential for handling file operation in multi-thread environment. These functions help to ensure that all threads within a process can safely read and write to the same file descriptor with interference. So let's consider where two threads, thread A and thread B, are attempting to read from or write to the same file descriptor. For example, thread A may execute L6 edit 306 set and thread B is 700 So this situation can lead to both reading the same record, which is not the intent behavior. So we have a solution to address this issue. We can use the pread and prewrite functions. So this function allows us to combine the setting of the object and the reading or writing of data into a single atomic operation. For instance, thread A can call pthread buf1 100 300, while the thread B call pthread fd pub2 100 and 700. This have the thread A read from offset 3 and thread B read from offset 700, ensuring that both threads operate independently and correctly. So here a simple code with use pread and prewrite function. You can see the result. Thread A read data. Thread A read data from the file at locale 300 and display the result data from the thread A. So this just means that the file may contain empty bytes or no data from previous write, since a specified buffer size is larger than the actual data. And thread B write to a file at location 700 with the content data from thread B and report that it has been successful. So this means that the threads can operate in parallel with thread A doing the reading and thread B doing the writing without any problems. So this program, so the importance of understanding how the threads interact with the I/O and the need to manage the current access to avoid data conflict and errors.